So before I start with introducing uncertainty in the EOQ model, what I'd like to have you do is work on this example. So please go ahead and pause the video, and when you're ready, we'll work through this problem together. So go ahead and pause the video, and again, when you're ready, go ahead and restart it. Okay, so hopefully you were able to use the formulas that we looked at on Monday to work through this, but we will work through it together now. So, first question is, how often would you order? Well, so what is that asking? So that's asking, what is the time between orders? And again, reviewing the slides from Monday, we can see that that formula will be Q over D. And so then we want to look at, do we know Q? No. Do we know D? Sort of. So let's go ahead and start with D. So D, we see that the constant demand, so it's known and constant, is 2,025 chips per month. And when we talked about the definition of capital D, we said that that would be the annual demand. So right now we have monthly demand, so let's go ahead and convert that. So we have 12 months per year. We can cancel out our units of measure, and we find that we come up with 24,300 chips per year is our annual demand. So now that we have D, we can focus on Q. And specifically, since this is an EOQ problem, EOQ means that we are looking for Q star. So Q star being a specific value of Q, we know that that formula is 2 times the annual demand times the ordering cost divided by the holding cost. Well, when we look, we just calculated D. The cost of ordering is going to be the fixed cost that we're incurring every time we place an order or do a machine setup. And so we see that that would be $500 for our ordering cost. And our holding cost based on annual interest rate of 15% of unit cost. So we see our holding cost will be 15% of our unit cost. And we see that each chip is $50. And so we see that it's $7.50 per chip per year. So this is already annualized. So now all we have to do with our Q star is plug the values in that we already know. 2 times 24,300, our annual demand, times our ordering cost, $500, divided by our $7.50. This is annual, this is annual. Those units of measure cancel out, and we find that we come up with our quantity per order would be 1,800 chips. So every time we place an order, that order will always be for 1,800 chips. So now we have our Q star, we have our D, so we can calculate our time between orders. 1,800 chips divided by our 24,300 chips per year. So we can see that we will place an order every 0.741 years. Now, oftentimes people will ask me, how do we know what time unit to use, or what unit of measure should we use? Well, we're looking at something like this. We want to try and put this in something that is fairly intuitive for whoever's going to be using this information. So you can ask yourself, if somebody came to me and said that I would need to place an order every 0.0741 years, Would that be intuitively obvious for you? Probably not. So then we can look at a couple other options. So we can take that 0.0741 years and convert that into months. And so we know that 1 year is, excuse me, 12 months per year. We need to cancel out the years, and we come up with 0.89 months. So that helps us quite a bit. So we know that they'll be placing an order just under every month, a lot more intuitive than this. We could also, if we wanted to, take a look at one more option, since we are given 52 weeks per year. So we can go 52 weeks for one every year, cancels out, and that would mean every 3.85 weeks we would be placing an order. Now, typically, I would tell you exactly what time unit I would want, but again, we can think of this. If we aren't told, then we would want to try and put it in something that's fairly intuitive for whoever's going to be looking at our information. So, and obviously, all three. If you aren't given a time unit, then technically all three of these are correct. So, the next question is, how many memory chips should you have on hand when you place an order? So, what is that asking for? So, how many memory chips on hand when we place an order? So, when do we place an order? We place an order when we hit our reorder point. Our reorder point formula is D times L. So, do we know L? Yes. It takes 3 weeks to receive an order. So, 3 weeks is our lead time. And so for D, we know that we had our annualized demand as 24,300 chips per year. So if I go ahead and plug those values in, my demand 24,000, and the reason for the little d, that little d doesn't necessarily have to be annualized. But what do we know that we need to do? Reorder point is simply a quantity, and so we want to make sure that we've eliminated all units of time. So we take our 24,300 chips per year, multiply it by our 3 weeks. Can we cancel these out? No, not the same. But again, what do we know? 52 weeks per year. So 1 year is 52 weeks. Weeks cancel out. Here cancel out. So again, no time unit is left, which tells us we're on the right track. And with the right numbers, we come up with 1,401.92, or we'll go ahead and round that to 1,402 chips. So we've now calculated our reorder point. And the third question is, what is the total cost, total relevant annual cost, which would be the sum of the holding and ordering costs. So we know that our total cost formula is equal to D over Q times our cost of ordering. So we have our ordering cost here, and then our holding costs is going to be our average inventory level, Q over 2, times our holding cost. And again, we already know our ordering cost is 500. We know that our holding cost is the $50 times the 15% annually, or $7.50. And we calculated D previously, and we calculated our Q previously. And if we recall, our Q was specifically our Q star, our EOQ was 1,800 chips. So then our total cost is going to be 24,300 chips per year divided by the 1,800. That will give us the total number of orders per year times our ordering cost of 500 plus 1800 over 2, our average inventory level, times our holding cost per unit per year. So when I calculate the total cost, when I calculate this, I get 6,750. Then I go to calculate this, but before I go to calculate that, what should we know that it should equal? Well, what does the EOQ formula do? The EOQ formula, again, we looked at the EOQ formula, which is derived from this. So we calculate the derivative, set it equal to 0, and then solve for Q. And so the EOQ formula is balancing the ordering cost and the holding cost. So therefore, these two costs, and again, going back to our, if we think back to our curves, we had our ordering costs, we had our holding costs, we have our total cost curve, and so where was the EOQ? The EOQ was at the intersection where the holding costs and the ordering costs curves meet. So we know that these should be equal. So now I can do this calculation. I come up with 6,750. Well, again, since these two numbers are equal, it tells me I'm probably going to be on the right track. Now, if these two numbers were different, it probably means that you did some calculation error or possibly put in an incorrect value somewhere. Because again, you should know at the EOQ you should have these two values equal. So we have our 13,500 for our total annual costs. Hopefully you did well on that. If you have any questions, please feel free to email me, and I'll be happy to answer any questions that you have on this. Going back to lecture slides. So we just answered that. And this model in inventory management is, the EOQ model specifically, is known as the QR model. And again, when we're thinking about inventory management, what are we looking at? We're looking at when do we order and how much do we order. So how much do we order is our Q. When do we order is our R, reorder point. So we have our QR system. And as I mentioned, in this class, we'll be only looking at continuous review systems and not periodic review systems, which would just require a small tweaking of the formulas, but don't want to get into that at this point. Okay, so now I'm going to relax the assumption of known and constant demand. So now what we're going to allow is some variability of the demand. And so as we're coming down, so instead of having a nice straight line right here, we have more of a jagged because of the variability. Now the average, on an average standpoint, the demand is constant, but the period to period is not constant. So there's variability from period to period, but the average demand would be constant. So we can think of this such as a normal distribution of the demand. So we're coming along, we have plenty of inventory to cover that variability, but then when we get down to this reorder point, from here to the time we receive it is what we're mainly concerned with. So when we place the order, the reorder point is supposed to be to cover the demand during the lead time. Well, if that demand is now variable, we can have a couple situations. One is the average demand over that time is the same as we expected. So if we expected 100 units per period to be sold, and it takes 3 weeks, for example, to receive an order, then we would expect 300 total units to be sold. And if so if one period it's 97, another period it's 100, and the third period is 103. Well, again, on average, we've met that, and so we would be exactly at 0. We would receive our Q in and proceed on with the next cycle. But we could also run into a situation where the average demand was less than our expected demand. And so again, going back to the example of 100 per period, so instead of getting that, let's just say that we got 95, 90, and then 100 in the respective periods. Well, then the average is 95 per period, and what happens? We'll end up with more on hand when we receive the new order. So we receive the new order Q. So we had some inventory left over. We receive it in. This is now going to be higher than just Q, because this Q was assuming that we got down to 0. We receive in Q. Now we're going to be Q plus whatever that difference was between what we expected over the lead time and what we realized, what was actual over the lead time. Conversely, we could also run into a situation where we had more sales than expected. So again, if we were expecting 100 per period, let's say that we had 100, then 105, and then 110 in sales. Well, that means that we ended up with 105 on average per period as opposed to our 100. So we would be in a backlog situation. We receive Q, we ship whatever the backlog was, and then whatever's left gets put into inventory. But obviously that would be less than Q by the amount of whatever that backlog amount was. Again, we could end up potentially with exactly 0. So how do we handle this? Well, if we just let it go, again, assuming normal demand, if we just let things go, then 50% of the time we'll have extra inventory at the end of the period, and 50% of the time we'll be short, statistically speaking. But companies may not want to have 50% out of stock. They want their customers to be satisfied at a higher rate, and so we need to look at introducing safety stock into our formula. Add a measure of safety stock to buffer. So, how do we do that? Well, let me go ahead and draw what we already know. We have our Q over 2. Again, I'm not an artist. We have our reorder point, and we have our 0 line. And we have our demands, etc. Okay? So now we want to introduce safety stock into this. So, so here's our current 0 line. Well, let's go ahead and introduce some safety stock into this. So what safety stock is a quantity. There's no time unit associated with safety stock. Just like with Q or R or even Q over 2. There's no time unit associated with it. Time. Okay. So the example I like to give is in my wallet. I have two sections. One area I keep my cash in. The other area right now is empty. Well, what I found, hypothetically speaking, what I found was last year I would end up having to borrow money from friends when we went out to dinner, and I didn't like that. And so what I decided to do was keep a certain amount of money in my wallet at all times, just to cover those situations. So, I took to take a $20 bill. I put it in that unused pocket in my wallet, and I leave it there. Well, at the end of January, I haven't touched it. How much money do I have in that little extra pocket? Still have the $20. After month 2, still haven't touched it. How much is there? 20. Month 3, month 4, month 5. December 31st, I go into my wallet. How much money is in that extra pocket? Still $20. As much as I would love for it to be like a rabbit and multiply over time, it does not. So, again, safety stock is a constant amount that does not change over time. So what I'm going to do is introduce safety stock into this diagram. So this will be my safety stock. So I'm going to change my 0 point. So instead of 0 being here, I'm moving it down to here. So if I have 0 here, then I have my safety stock amount. What does this number become? Well, 0 plus safety stock. So it would become safety stock. This R previously was based on this being 0. Well, what would this value now be? It would be R plus the safety stock. Q over 2. So Q over 2 was this amount previously. Now what is it going to be? Q over 2 plus safety stock. Then I have my Q was from here down to my 0 line. What is it now? I have the Q plus my safety stock. So again, by adding safety stock does not have a unit of time associated with it. It's just a constant amount of inventory that I'm going to have on hand, on average. So here, we can see that I would be dipping into safety stock, but if you recall, 50% of the time, I will also have it where I have a little extra, and I come up, and then I continue on. 50% of the time I will run into some back orders. 50% of the time I'll have some left over. And again, normal distribution, looking at long run averages, these will balance out back to this line. So the safety stock over time will remain constant. So again, all I've redone here is introduced safety stock into this and then altered these values accordingly. Why is that important? Again, this is looking at introducing safety stock. What's the demand during the lead time? So I place the order. When do I receive it? So again, safety stock is a fixed amount, and we can calculate safety stock based on statistics. Again, we're going to assume a normal distribution for this course when calculating safety stocks. So initially, going back to Monday's lecture, the reorder point with known and constant demand, we had the reorder point being D times L. And as we saw in our new diagram, when I add variability and I add safety stock into it, the reorder point will be D times L plus safety stock. In this case, the safety stock is the equation for safety stock is Z times the standard deviation of demand times the square root of lead time. So I have D times L plus safety stock. Again, coming back here, what do I see? We'll have our D times L. So the reorder point before was D times L. And now it's going to be D times L plus safety stock. Okay, so what we calculated here graphically and intuitively is what we're seeing here in our formula. So again, standard deviation of demand. So that will be, again, when we're looking at a normal distribution, we'll have our expected demand and then our standard deviation, or the variability that we're going to be analyzing. And then we have our lead time. So then the question is, what is Z? How do we find that? Well, Z is found from the standard normal distribution. So when we're looking at the standard normal distribution, the area under the curve up to the service level that we want to achieve is going to be 1 minus alpha. 1 minus alpha being the probability of not stocking out. Probability of not stocking out. Where alpha is over on the tail, and that is going to be the probability of stocking out. So we will find the Z value corresponding to the service level that we want. So if I want to allow no more than 2% stock out, that would be 2% being my alpha, the probability of stocking out. That means that my probability of no stock out would be 1 minus 2%, or 98%. So that would mean my service level, I would be servicing 98% of the orders based, and again, I will want to find the Z value so I can calculate the safety stock that would be needed to satisfy that requirement. And companies will typically set that internally based on various dynamics, what type of product it is, what their corporate strategy is, etc. So, and the great thing is, with the service level, we can take the service levels, we can look at our standard normal distribution table, and it gives us all these values, and I just kind of summarized them here in a nice table. But you can find the Z values on the standard normal distribution table. So here we have our expected annual demand. Again, since it's telling, so now we're looking at expected value instead of a known and constant demand. So that's our expected value, given our other values, days per year, etc. And so we want to calculate the economic order quantity and reorder point. And here we see our stock out risk of 5%. So what I'm going to do is ask you to once again pause the video and calculate the EOQ and the reorder point, and the reorder point will include the safety stock value. Once you've done that, go ahead and restart the video and we will work through it together. Okay, great. So hopefully you've had a chance to calculate that. And so the EOQ is the same as it was before, 2 times the annual demand times the cost of ordering divided by the cost of holding. That formula has not changed because we're just putting in the expected demand instead of the known and constant demand. So this formula does not change. So we put that in and we find that Q star, or EOQ, is equal to 365.15. Now, the next question would be how to calculate the reorder point. The reorder point is going to be D times L plus our safety stock. So we know our safety stock formula is Z times the standard deviation of demand times the square root of L. So our D, we had 10,000 units per year. We said that there was 365 days per year, and our lead time was 10 days. So what do we see? Our units of measure cancel out, and so we just come up with a quantity, number of units on this side. Then here we have the 1.65, and we calculate the 1.65 because we want to find the probability of not stocking out. And so the probability of not stocking out is 1 minus the probability of stocking out. And as we look back here, our stock out risk is 5%, so 1 minus 5% would be 95%. We look at our table, and we see that it's going to be 1.6, our Z value will be 1.65. Plug in our 1.65, we're given our standard deviation of demand here. Now, this is in daily demand. So the standard deviation of daily demand is 7.9 units. Now, the question would then become, do I need to convert that to annual? Well, let's take a look. What's our lead time in? Our lead time is in days as well. So we have days here, we have days here, and when we come to this formula, that time unit will cancel out. So as long as the time unit is canceling out, we're okay. We don't have to convert anything, because since they cancel out, and again, reorder point is simply a quantity, no time associated with it. Time was eliminated here in these units by dividing by 365 and then multiplying by the 10 days. And here the days are canceled out here and here, and so then we're okay. We don't need to convert as long as the time units for the standard deviation of demand and the lead time are the same. Otherwise, we would then have to make a conversion, and you would want to convert the lead time value rather than the standard deviation of demand. It's just simpler, more simple mathematically, and if you're interested why, feel free to drop me an email and I'll be happy to explain. Okay, so we calculate our demand during lead time, the D times L, 274. Then we calculate our safety stock value, the Z times the standard deviation of demand times our lead time, 41.22 units. We add that together, and so our reorder point is going to be 315 0.22 units. So again, with our continuous review policy, as soon as we get to 315.22 units, we will immediately place an order for Q. And again, our Q is 365.15 units. So that is our new QR policy. So then when we ask the question, how much safety stock am I holding? Well, we've already calculated that. Safety stock is just this term, which is this value, which is simply this value, 41.22. So our safety stock is 41.22. Now, what's our average inventory level? Well, what is average inventory? It's going to be Q divided by 2. So Q divided by 2, we already calculated Q, so we'll take our 365.15 divided by 2, and we get 182.575 units is our average inventory level. Next, suppose I want to increase the service level to 99%. Intuitively, without necessarily putting the numbers into the formula and calculating it, just by looking at the table on the left, what would be the effect on our safety stock? Well, again, using our intuition, we know that our standard deviation of demand hasn't changed, our lead time hasn't changed, so those aren't going to be impacting our safety stock value. Only the service level is changing. So we go from 1.65 to now 2.33. So again, without even putting in the numbers, and we certainly can, but we can see that the effect on safety stock would mean that we would have to carry more safety stock. Now, next question, what would be the impact on our total cost? Well, we would be increasing our total cost because we would be increasing our safety stock. And in our new total cost formula, by the way, so our total cost formula, we had our D divided by Q, number of orders per year, times our cost per order, plus we already had our Q divided by 2 times our holding cost. But again, when we look at this, what's our average inventory level now? Our average inventory is our Q divided by 2 plus our safety stock, this base amount. So we're always carrying this, and so we're paying holding costs on this safety stock all the time. And the Q divided by 2 is just the individual cycles. So I need to add that in. So I have my safety stock times my cost of holding, or I can simplify the terms, D over Q times our ordering cost, plus my holding cost, here and here, Q divided by 2 plus safety stock, which is what we have here. Okay, so we can adjust our total cost formula. So therefore, as we increase our safety stock, when we go from 95% to 99%, what happens to our total costs? That increases. So again, as the managerial insight that we'd have to consider is that additional cost for holding our safety stock going to be worth it versus what our company is trying to achieve in terms of satisfying customers at the different levels, 95 or 99%. So we can see that this safety stock has an impact on us. Now, to look at that a little bit further, as we just saw, safety stock is not free. So we've altered our formula. We have our new total cost formula. We put the values in, the $10 ordering cost, 10,000 units per year, divided by our EOQ value that we calculated previously, our holding cost, Q divided by 2 plus my safety stock. So my total cost with safety stock is $609.55. If I eliminate this term, I eliminate the safety stock, then my total cost without safety stock is $547.72. Or again, we can see that basically, so the difference is our cost of safety stock, $61.83, which means that our safety stock has increased our total costs by 11.3%, and that's at the 95% level. And so we can recalculate and see that increase is even higher, percentage increase is even higher when we go to a 99% level. So again, we can then quantify the value of our safety stock and then make the decision of, is that safety stock, is that service level worth this amount of additional cost? Okay, so some observations as we just looked at. So the higher safety stock means it will be carrying a higher average inventory level, because our average inventory level now will be Q divided by 2 plus safety stock, which then translates into total higher holding costs, but we'll have better service levels. So again, as a business, we have to decide if that's going to be worth it. We see that safety stock impacts the reorder point being D times L plus safety stock. But we see that the standard deviation of demand, that variability does not impact the EOQ. Instead, we still use the expected value of the annual demand, so that doesn't change. So our EOQ formula does not change. So again, safety stock impacts our reorder point, but not our EOQ. And then again, looking at just trying to help build some intuition here with this question. In order to get high service levels with low amount of safety stock. So I want high service levels. Well, as this Z increases, if we want Z to increase, our service level, high service level, we want our service level to increase, but we want our safety stock to decrease or be as low as possible, low amounts of safety stock. So if I want this to be low, this to be high, how do I balance that equation? Again, not looking at numbers, just if one number on this side of the equation increases and this one we want to decrease or stay the same, what has to happen through the combination of these? Well, naturally, if this is going up, we need this pairing to go down. So we can look at decreasing the lead time with our suppliers, which is often, we often hear about that, lead time reduction initiatives within a company. Or we can try to decrease the standard deviation of demand. This tends to be a little bit harder, but it is possible. So again, just trying to build some intuition and why companies do some of the things they do, such as lead time reduction, because again, that helps them be more responsive, which helps reduce the amount of inventory that they have to carry in terms of safety stock. And even when we look at the reorder point, we have D times L. So I can actually get a double benefit by reducing lead time, because I'm reducing the L from the D times L term, plus I'm reducing the L in the safety stock